Lecture 16, so we are way into the downslope of this course. Hopefully it'll start getting a little bit easier and easier now. Today we will continue to do a little bit more with Navier-Stokes equations. If I get through what I have planned today, then next class I want to present to you an introduction to computational fluid dynamics. And you'll have to do a little bit for your next homework in regards to that. Do you remember your MATLAB from the, what is it, the course EK 127? Yes? You learned how to do loops in MATLAB, iterations? Yes? That's basically all you need to remember, to write some very, very short little script that will introduce you to the techniques of computational fluid dynamics. That's next class. Before we start this class, let me just remind you what we did in the previous one. We were discussing Reynolds number and the importance of Reynolds number, and we said it represents the ratio between inertia and viscous effects. And so we discussed a little bit what it means to have inertia and viscous effects competing for, to dominate in a flow. And we saw some movies there to illustrate this idea of inertia and viscous effects. Then we said, well, if you go to really, really low Reynolds number, you have what's called the creeping flow. In really, really low Reynolds number, what you have is that the Navier-Stokes equation simplifies quite a bit, basically because that nonlinear term that appears there. The nonlinear term, which there in the picture of Obama, is right there. I can see it. There it is, the nonlinear term. That's the one that causes problems. Because there is, in fact, no standard method for nonlinear partial differential equations that one can apply. If the partial differential equations are linear, and this perhaps you will see when you take a partial differential equations course, if you do, I hope you do, you will see, and you will certainly use this in heat transfer. For linear partial differential equations, we can use the principle of superposition. And the principle of superposition allows you to find solutions in many, many complicated situations. But for nonlinear equations, we can't use that. There is no general method that we can use for nonlinear PDEs. So that's a term that causes a lot of trouble in both the Euler and the Navier-Stokes equations. But for creeping flow, that term can be neglected. Basically, inertia terms can be neglected. That term is related to inertia. And the flow is completely dominated by viscous effects. And in that situation, we were able to find some solutions. And there's a very, very famous result that we presented last class for the case of a very small particle, a spherical particle settling in a fluid. And that would derive the drag force, and there's a terminal velocity, and that's called Stokes' law for a sphere. Very famous result. We also discussed the distinction between laminar and turbulent flow. In sort of more intuitive effects, a laminar flow is characterized by being smooth. The flow, can be steady and quite orderly. Turbulent flow is never steady. Turbulent flow is characterized by chaotic motions and, eddies and so on. It's never steady. So then we started discussing the exact solutions to Navier-Stokes equations. Some very particular cases where, because of symmetry, for example, geometrical symmetry, the nonlinear term again cancels out, and then we can find a solution. And we saw first the case of flow between two parallel plates. For your information, the flow between, here it is, the flow between two parallel plates is also discussed in the textbook by Post on pages 179 to 182. Now, the derivation shown in the book is rather different than the one we saw in class. I find it wasn't to me as clear. I thought it was a little bit more convoluted, but it's another way. Every problem has at least 5 ways of being solved. So you can find there an alternative derivation. The important thing about the flow between parallel plates is that it's a flow driven by pressure. By a pressure gradient. appearing here. This is the solution that we derived. I did say that I wasn't sure whether to use the word Poiseuille. I introduced it as Poiseuille flow, and then I sort of wasn't quite sure if it was correct to call it Poiseuille. It is true that some people call it two-dimensional Poiseuille flow, but in fact it's one problem that was never mentioned by Poiseuille himself. So it's more standard to call Poiseuille flow, and we will discuss it in a moment, the flow, laminar steady flow in a pipe, so in the circular symmetry in a pipe. But people do call this Poiseuille flow as well because it results in a parabolic profile, the same as the other one. They both result in a parabolic velocity profile. This one can be considered to be laminar up to a Reynolds number of about 1,000. And beyond that, it will become turbulent, and you no longer see the parabolic velocity profile. You can no longer apply any of the derivations that we did last class because it's unsteady, and so the equation is different. The derivation we did last class was for steady flow and so on, so we had a lot of simplifications that we were able to do. Then we discussed the Couette, the case of Couette flow. For the case of Couette flow, which unlike the previous one is driven by, this one is driven by viscosity, driven by viscosity, by viscous drag. It is the same case of two parallel plates, infinite parallel plates, so you can look at it as a two-dimensional flow. The only difference is the boundary conditions. So that illustrates very clearly how the same partial differential equation will give a different solution if you have different boundary conditions. This is exactly what happened here. We had the bottom plate stationary and the top plate moving with the velocity u. And the top plate drags the fluid by viscosity. Now, the solution we obtained looked like this. We wrote it in a non-dimensionalized form where capital U is the velocity of the top plate, little u is the actual distribution of velocity inside the fluid. So u, small u, is a function of y, where y was in the direction of the width, the sort of the distance between the two plates, and x was the direction of the flow. So the solution that we obtained looked like this. It was u over capital U equals to y over b, where b is the separation between the two plates, minus, let me call it c, a constant, y over b, 1 minus y over b, where this constant c is equal to a parameter, minus b squared, everything is known here, divided 2 mu capital U, the velocity of the plate, times dp dx. Yes?
Should b squared be positive because you have a minus in front of c? You have a minus in front of c in the equation.
Yes, you're right, yes. The whole thing, I put the minus sign over here, so we don't have two minuses there. Okay, thank you. Very good. You're keeping track of my typos. Excellent. Saves me from putting lectures on iTunes with typos and mistakes. So you can see, of course, that if the pressure gradient was 0, the flow is driven entirely by viscous drag, and you have a linear velocity profile, which is the red line that I've put there. For different values of dp dx, you can plot this function here, and it's going to have these different shapes as a function u of y, or non-dimensionalized. In this case, it's non-dimensionalized. You see here y over b, u over capital U. So everything's non-dimensionalized. Now you can think about that velocity distribution as a superposition of two parts. A linear velocity profile this term over here, y over b, linear, which is, this linear velocity profile goes from u equal to 0 at the bottom plate to little u equal to capital U, the velocity of the top plate. The linear velocity profile plus a parabolic distribution. The second part here is parabolic, you see? That depends on the magnitude of the applied pressure gradient. You see? So we have these two components that could be driving the flow. If the pressure gradient is 0, the flow is still moving because of viscosity. In the previous example, where we had the flow between two parallel plates with the two plates stationary, if there's no pressure gradient, there's no flow because it's only driven by pressure. In this case, there is flow with no pressure gradient, but if you add a pressure gradient, that contributes, again, the parabolic component of velocity, if you will. It's a way to think about it and understand it. So the shape of the velocity profile depends on basically this parameter here, but the contribution of this parabolic profile depends on the magnitude of the pressure gradient, as you can see here. Okay, this is for co-ed flow, and I'm just explaining a little bit more the result that we. Yes, you have a question?
Yeah. Oh, maybe you explain this one more time. Can you explain why it's a flow driven by distance?
Because basically the top plate is just dragging the fluid along because of the no-slip boundary condition. The top plate is moving. And so I'm using the words rather loosely here. I don't mean it drag as the force of drag that we used to talk about in the sense of flow around immersed bodies or anything like that. But it's a viscous drag. It's a shear. It's a wall shear that causes the fluid to stick to that wall and want to flow with it, right? And causes the fluid to stick to the bottom wall and want to be stationary with it. And that causes this linear profile between u equal to 0 and u equal to capital U. And that drives the flow, even if there's no pressure gradient. Is that clear? Yes?
The non-dimensionalization is for what purpose would we use that? Why is that non-dimensionalized?
It's a technique that we use to be able to make a plot that is representative without taking away the geometry of the B, for example. You want to take away the dependence on the width, B, and the dependence of the magnitude of U. And then this profile is pretty much applicable to the whole set, the whole family of flows of this kind. It's a common technique that one uses to get something that, regardless of the magnitude of that velocity, for example, these profiles are going to be similar from one flow to the other flow. That's what one wants to exploit. Yes.
Is this steady state?
This is steady state. We used the property of steady state to simplify Navier-Stokes equations and be able to obtain this result in that class. Yes. No more questions? So co-ed flow, as we see it here, it's of course a flow that would be. It's a flow configuration that would be very difficult to realize in real life because we're assuming that these are infinite plates, right? So it would be very difficult to do this to demonstrate this experimentally. So Sir Geoffrey Taylor came up with an idea of looking at instead the flow between two concentric cylinders, and if there is a gap between the two concentric cylinders, as shown here in this cartoon, that is very thin compared to the diameter of the cylinders, then you can sort of neglect the effects of curvature, and it's almost like having an infinite, the same situation as two infinite plates. Okay, so he suggested to look at this case. It's called Taylor-Couette rather than just Couette. And in this case, the solution that we just derived, in fact, is a good representation of what's happening there between the two cylinders. Of course, you can think immediately of the applications that this would have in terms of lubrication theory, right? This is the typical situation that you may have. A very narrow gap, for example, well, they're not rotating, but if you think about the cylinders in a internal combustion engine, you also have a very narrow gap that's filled by oil, right? A lubricating fluid. In that case, it doesn't rotate. It actually is moving axially. But there are other situations where you have a rotating shaft which is lubricated in this way. So you want to calculate things like the torque required and so on. So the flow in this narrow gap between two concentric cylinders is approximated very well by the Couette solution. So in this situation, we have a let's use R0 for the outer cylinder radius. Ri for the inner cylinder. And we had before B as the separation between the two plates. That's just going to be RO minus RI. And the Couette flow is going to be obtained if the gap is small. So we want RO minus RI much smaller than, say, RI for. So if the gap is small, then we can use Couette flow solution. So then, since this is rotating with an angular velocity omega, the velocity U is going, capital U, the velocity of the top plate, the equivalent of the velocity of the top plate is going to be equal to Ri times omega, omega being the angular velocity. And for example, there was a homework last year in which we asked about this problem. And the homework said the inner cylinder is fixed. Find an expression for the torque required to rotate the outer cylinder with an angular velocity omega. Express the answer in terms of the geometry of the system, the viscosity of the fluid, and the angular velocity. That was the question from last year's homework. So the torque which must be applied to the outer cylinder to overcome the force, what force? The force of viscosity, the shear stress which is caused by viscosity, right? So suppose we look at the force due to viscous shear. I'm going to delete the cartoon now. Have you made a little cartoon there in your notes that I can delete this one? Somebody's still drawing, so I'll leave it up a little bit. So the force is going to be the shear times an area. So we need to find the force due to viscous shear, and then let me just write, this is our question, force due to viscous shear, and then the torque required to overcome that viscous shear. Can I erase the cartoon now? Yeah, okay. This is the question. So what would be that torque? Well, the torque, let's call it T, is going to be equal to, let's call it dt, a small differential of torque is going to be equal to R, the outer radius, multiplied by the differential of force. And the differential of force is going to be the shear stress times the area. So dt is equal to R0, RO, outer, times the shear stress, tau, and the area, RO, some sort of length perpendicular to the page, to the cartoon that we drew, and a d theta. That would be our area where that shear is being applied. So it's r squared tau, that's a square, not much better there, it's a square, believe me, tau, and L d theta. So the total torque would be, yes?
Wait. You have two terms for torque?
Sorry, what?
Is that dt and the change of torque?
It's a small differential of torque. I'm going to have to integrate.
But then your tau over there is torque also?
Tau is the shearing stress.
Oh.
So from, if you recall your definition of viscosity, tau, forgive me that these letters kind of look similar. Tau is a Greek letter, tau, and it's our shearing stress, so mu du dy, right? And u, immediately we can start working with this. U is the case here is there's no pressure, so it's just the linear component of Couette flow. We had capital U, for the infinite flat plates, we have the velocity of the flat plate times y over b. That was the linear profile for, if you recall, no pressure gradient. So that's our solution for U. So we can get du dy, and immediately we can get the shear stress. So the shear stress, and I'm going to make it a little more curly here, but so that you are not confused, the Greek letter tau is simply going to be mu times capital U over b. Capital U, the velocity of the top plate for the infinite plates section, but we can use our expression here for the rotating case. So b is also related to the radius. So all of this can be written in terms of the cylindrical geometry that we have now, where capital U, the velocity, is r(I) omega, and b, the distance between the two plates, in this case is r(O) for outer cylinder minus r(I). So we have here the shear stress, and we're going to need to integrate that between 0 and 2 pi to obtain the total force around this whole cylinder. So torque, capital letter T in Latin alphabet, is equal to, where is it, r squared L integral between 0 and 2 pi of tau d theta, but tau doesn't depend on theta, so basically we can write it immediately. It's the simplest possible integral, r(O) squared L tau, the Greek letter tau here for shear, or let me just write it immediately what it is. Ooh, some sort of, sorry? The omega is a constant. It's the angular velocity of this whole thing. It's supposed to be rotating at a fixed angular velocity. L is the cylinder length, of course, perpendicular to the picture, right, that we drew, perpendicular to the paper. And so everything is known. We can just write L, well, let me just write tau here to make it easier, and it's 2 pi, right? The integral of d theta between 0 and 2 pi. It's just 2 pi minus 0. And so we're ready It was not too hard. Our let's write the 2 pi in front since it's just a number. 2 pi times r outer squared L and the shear stress, which is mu Ri omega over Ro minus Ri. And here is our result. L is the distance. So really what we have, we're looking at a cross section, right? But what we have is, if you look at the cylinders, some very long cylinders, and perpendicular to our original sketch is that L. So it's the full area of the cylinder where the whole force is applied. So this is what the situation that it wants to represent is really an axis, say, of some sort of rotating machinery that is lubricated by a very thin layer of some fluid. And that's going to be the torque required to maintain a constant angular velocity omega. The dA is used here, RL d theta. That's a small. So if I make a picture here, what we have is if I make another picture again and exaggerating the distance between the two cylinders. Oh, I know my. So what we have is this is the inner one, and the outer here. So we have some angle d theta, right? And the distance, this area, we're going to integrate between 0 and 2 pi, and it's multiplied times L in the perpendicular direction to that picture. Yes?
So what Taylor said about wet flow is that he takes that rate, if he assumes a flat flow instead of a cylindrical flow, then he can go back to the wet flow and eliminate the C term, take C to 0, constant.
The C term is 0 because we're assuming that there's no pressure difference all around here. Where basically you're taking that flat geometry that we were looking at and turning it around on itself to close the cylinder. And we're using the Couette solution with C equal to 0, assuming that there is no pressure gradient along the cylindrical coordinate here. So we have, that's why we have this solution for the velocity, which is only the linear component of Couette flow, if you recall. If you look back at your Couette solution, it's only the linear component. So this one is already taking into account that dP dx is equal to 0.
So then the two assumptions are circular to linear and dP dx is 0.
Mm-hmm. And that applies for very, very narrow gaps in comparison to the diameter of the cylinder, where the curvature really effects are very small. Good? Yes? No questions? Okay, so the last one we're going to do for the exact solutions of Navier-Stokes equations, as I promised, is Poiseuille flow. Poiseuille was actually, interestingly enough, he entered the engineering school in Paris at the age of 18, but at that time, for political reasons, the whole school was disbanded and closed down. I don't know what political story happened there. And he never again studied engineering. He went on to get a medical degree. He was a physician. But he dedicated a lot of his life to studying. His goal was to understand the flow of blood in small capillaries. And so he did very thorough experiments throughout many years about the flow of capillaries, the flow of fluids in very thin and narrow tubes. I have found a little historical paper that I'm going to put in Blackboard for you if you're interested to read, because it's an interesting story. And he practiced medicine for a little bit, but in fact, really, it's not very clear because there's not much, many records about his life. But what is clear is that he dedicated years of his life to study, to do very methodical experiments, and obtain these results, which now bear his name, of the flow in steady and laminar flow in circular tubes. And he was interested in looking at the effect of different fluids. It was interesting at the time, there was not really a very thorough knowledge about viscosity. In fact, things like the no-slip boundary condition was not entirely accepted. People still didn't really know if they could assume no slip as a boundary condition. And these results were, in some circles, used as a demonstration of the no-slip boundary condition, because everything was explained in terms of the results. If you assumed in the mathematics that there was no slip boundary condition, things would only match. The theory would only match the experiment if the no slip boundary condition was true. Posey was interested in looking at the effect of different viscosities. He didn't really know it was viscosity. He just knew it was a constant that depended on the fluid and also depended on temperature. In his results, it was not clearly written as viscosity. But it seems that he was interested in the possibility of affecting the flow of blood through medication. It seems that this was sort of his goal. So he was really a doctor, a medical doctor at the time, who turned out to contribute quite a lot to engineering. In fact, Posey's law, I think, is the only sort of engineering fluid mechanics result that is well known in the medical community. To this day, is the result that they use in all sorts of applications, medical applications. So it's quite interesting in that sense. So how do we do this? Well, we need to use, as I said, the Navier-Stokes in cylindrical coordinates. I'm just going to flash them at you like that, and then I'm going to make them disappear. And basically what we do is, we need to write all of we write the velocity in terms of, let me write it this way, like a velocity vector. We write the velocity vector as a component in the z direction, a component in the theta direction, and a component in the radial direction. So we have Vr in the, this is a unit vector in the radial direction, plus V theta, where the unit vector in the theta direction, plus Vz, a unit vector in the z direction, which would be equivalent to our unit vector k. So you write the velocity in this way, and you can find now all of your differential operators can be written in this coordinate system, and you can certainly derive the Navier-Stokes equations in cylindrical coordinates. And these equations, the Navier-Stokes equations in cylindrical coordinates, are in the textbook. So you put a little flag there on the page to look it up when necessary by post, page 182. And for those of you that have, what is the other one? That Munson? It's on page, well, I don't have the page, but I have the section. So you could look it up. It's the section. I guess it depends on, the page depends on the edition, but the section is 6/128 according to my notes here. Okay, so we have our Navier-Stokes equations, but we look at the situation that we're looking at. I'm not going to derive the Navier-Stokes equations in cylindrical coordinates. Of course, we're just going to take them for granted for the purposes of this exercise here, we're going to look at this pipe, right, where we have the radius of the pipe is going to be capital R, and we have, from the center we have, let me use green for my coordinates. In this direction is Z, and then we have, at whatever point, we will have a velocity Vz in this direction, right? But for the flow, steady laminar flow in a pipe, we have no radial velocity and no azimuthal velocity. These are 0. So if you're looking at your Navier-Stokes equations, everything that have v theta, or it's u in my equation here, is 0. So that's 0, that's 0, that's 0. All of these are 0 because u azimuthal is 0. And so on. This is with the same procedure we used before. VR is 0, or UR is 0, so all of these are 0 also. This is 0, UR is 0, and this is 0. So basically you see the equation simplified quite a bit. So I'm just going to write the result. We have our dpdr remains with only our gravitational term. Everything else is 0 from the first equation. And for the theta one is the same thing. We only have the d theta with possibly the component of the gravitation in that direction. Everything else is 0. And then we have only in the z direction we have a component of the velocity z. But velocity z, yes. So I'm going to now erase that. I'm going to write these simplified equations. Okay. So my equations disappear. You saw is the same process that we used before, and you can see that the equations look awful, but the symmetry allows us to simplify them quite a bit, and this is how they look like after the simplification. In the r direction we have 0 equals to minus rho g, and we're going to write immediately the component in that direction of g is multiplied by the sine theta minus dpdr. In the theta direction is the same thing, minus rho g cosine theta, and the pressure, except we have a 1 over r because of the derivative with respect to r term of the gradient has a 1 over r. This is what I was saying a little while ago. You have to write down your gradient operator and realize that there's a 1 over r that appears in the cylindrical coordinates. So these are quite easy. And finally we have the equation in the z direction where we have the pdz. So the z direction goes in the axial direction. So there's no pressure gradient there. Oh, well, sorry, there is a pressure gradient. There is no gravity there. Plus our viscous term mu, 1 over r, ddr, r dvz, dr. Because basically from these guys here, I did not scratch out all of the things that needed to be 0 in the previous equation. From these two things we have that if we apply continuity, gives me that dv z dz is equal to 0 when I apply continuity with these two guys being 0. Very similar to the cases we did before, except now we have cylindrical symmetry. Makes sense so far? I know I'm going, I'm not doing all the details, but it should ring a bell to the ones that we've already done and seem similar. So that, yeah.
Wait, so you're saying that by continuity the velocity of the z direction or the partial velocity of the z direction is 0?
Yes, the continuity equation, remember, is for an incompressible fluid is this. Okay?
Right.
So
but then the initial assumption is that we only have flow in
The flow is only in the z direction and the velocity is non-zero, but the variation of the velocity in that direction doesn't change. So if a particle is in the axis location, say, and it's moving along in the z direction, its velocity is always the same. That's what we're saying. Is the velocity is in another position in the radial, inside the tube, as it moves along, its velocity is always the same. The flow in that direction is steady.
Isn't that the same thing that we get just by saying it's steady flow?
Well, things could be steadily accelerating, for example. And as I move along the flow, it could be getting faster and faster. Suppose that the pipe was inclined, and there's gravity, and so the flow is actually accelerating in that direction. This is not happening here. That could still be steady, in the sense that the partial derivative with respect to time is zero. Remember the definition of steady. We had two forms of acceleration. Remember, this is a very important concept, very important. We have two components in the acceleration. One is the change in velocity with respect to time, and the other one is the change in velocity as a particle of fluid moves from one location in the flow to another location of the flow. And we've done that on the board as well in the breaks, again a couple of times, if you recall. We're applying the chain rule to the velocity, and because, the chain rule to the velocity as we take the derivative, because the velocity depends on both space and time, you get all these partials, remember? And the dv dt, partial of the velocity with respect to time, is the unsteady term. If that term is zero, we call the flow steady. But a particle itself could still feel its velocity changing when it moves from point A to point B. Because v, the velocity, is a field. It changes value with x, y, z. It's a different value in every point in space, potentially. And this is what happens here. This is not what happens. Actually, in this case, we don't have any acceleration in this space. In this case, in addition to being steady, the particle of fluid as it moves along doesn't experience any convective acceleration. All acceleration is still here, both unsteady and convective acceleration.
Sorry, one more clarification. The del operator is just in respect to t.
Say again?
The del operator, is that just taking partials with respect to t? That's why you can say that?
The del operator is actually the contrary, always partials with respect to space. And so, if you recall in our acceleration definition, this is very important, okay? I want you guys to go back and study this part and read it and think about it later, because this is extremely important in fluid mechanics. And if you take your advanced fluid mechanics, this will come up over and over again. Okay, if you looked at the acceleration, we had two components, the partial of velocity with respect to time, and this term over here, which is the derivatives with respect to space. But we have this dot product between this del operator and velocity. So this guy over here, and I'm going to take the time to write this one out because it's important, only this term over here, if I write it in Cartesian coordinates, it'll be u sub dv dx plus v dv dy plus w dv dz. So it contains the spatial derivatives, and it represents the convective acceleration, the change in velocity that a particle of fluid experiences just because it moves from one place in the fluid to another place in the fluid. If a particle were to instantaneously teleport from A to B, its velocity would change because v is different in all points in space. And this is what we call the convective acceleration. And these concepts are being used over and over and over again in this section of the course. We've continuously cited local acceleration, convective acceleration, when we looked at the different situations of, simplifying Navier-Stokes equations for parallel flow between two plates, and so on. All the different cases. We looked at the geometry characteristics, and we're able to cancel out some terms because we think about steady, we think about the flow not having convective acceleration, and we immediately know which terms to cancel out. So you see here, all of these terms in the left are 0 because there's no local acceleration and there is no convective acceleration. All of those terms are 0. This is very important that you take the time when you're doing your homework and you're actually studying for the exam. This is a crucial concept that you need to make sure that you mull over until it clicks, okay? I want you to take the time to go back to that class when we did the acceleration and do it again on some scrap piece of paper on your own, and carry out those derivatives and do the chain rule and think about those things that we've discussed in class, because it's very, very important. Yes?
So then steady is dV dt equals 0,
Yeah.
and laminar is del dot d equals 0.
This is 0 in the steady case flow. This being equal to 0 is not exactly equivalent to laminar. It is in the case of flow in a straight line, but the flow could be laminar and be kind of sinuous as well, and then you would have some sort of acceleration because remember the v is a vector. So if v changes direction, then this guy is not 0. It could not, Okay, let's take a little break now, and we'll finish this after the break.